Today's lesson will cover regression lines. After this lesson, you should be able to make predictions using regression lines, keeping in mind the dangers of something we're going to call extrapolation. You're going to be able to calculate and interpret a residual, and you're going to interpret the slope and the y-intercept of a regression line. Let's start with just the basic definition of regression lines. When the relationship between two quantitative variables is linear, so we're talking about two variables that we've measured something numerical about, we can use a regression line to model that relationship and make predictions. A regression line is just a line that describes how the response variable y changes as the explanatory variable x changes. Regression lines are expressed in the form y hat, which is what that little arrow is pronounced as, y hat equals a plus bx. Y is pronounced y hat. It's the predicted value of y for a given value of x. So pause your video now and take a minute and write down some of these definitions here. You want to make sure that you put that the response variable is y, the explanatory variable is x. You want to write down the equation for your regression line, and you want to write down that y hat is the predicted value of y for a given value of x. In the regression line, y hat equals a plus bx. A is the y-intercept, b is the slope. The y-intercept, a, is the predicted value of y when x equals 0. The slope, b, of a regression line describes the predicted change in the y variable for each 1 unit increase in the x variable. What we're talking about here is just slope-intercept form. The y-intercept is your starting point, and then it either increases or decreases some amount based on the slope. It's very important to use the word predicted in the interpretation of the slope and y-intercept. Otherwise, it may seem that our predictions will be exactly correct, and you're going to find that that's typically not the case. When the relationship between two quantitative variables is linear, we can use that regression line to model the relationship and make predictions. So we've got our regression line here. We've already written down our definition, y hat equals a plus bx. We're going to note that this is just the equation for slope-intercept form in disguise, y equals mx plus b. We switch these around so that the y-intercept comes first because that's usually your starting point, and then you either add or subtract some amount based on that slope. So let's take a minute and look at an example. Everyone knows that cars and trucks lose value the more miles they are driven. Can we use that information to predict the price of a Ford F-150 if we know how many miles it has on the odometer? So the odometer is the thing that keeps track of how many miles your car has on it. A random sample of 16 Ford F-150 Super Crew 4x4s was selected from among those listed for sale at autotrader.com. The number of miles driven and price in dollars were recorded for each of the trucks. Here's a scatter plot of the data along with the regression line. So here's our regression lines. They've already calculated that for us. We don't have to calculate it ourselves. X is our miles driven and Y is our price. So X is our explanatory variable. We're looking at miles driven to try to predict the response variable of the price. We're going to try to predict the cost of a Ford F-150 that has been driven 100,000 miles. So here's what we came up with. All of these dots represent one truck. So that's one truck that had under 40,000 miles, and it's going to sell for somewhere between $25,000 and $30,000. The regression line has been calculated for us. There it is. The y-intercept is 38,257, and the slope is 0.1629, and don't forget about the negative there. So they calculated the regression line for us. We need to be able to interpret that regression line. The y-intercept is 38,257. Let's interpret that. What that means is the predicted price of a Ford F-150 that has been driven 0 miles is $38,257. Remember that in a y-intercept, x is always 0. If we were to put that as a point, it is 0, 38,257. Your interpretation for the y-intercept should always include the word predicted, and it should always include the number 0 there. So the predicted price of a Ford F-150 that has been driven 0 miles is $38,257. Now let's take a look at our slope. That's the number in front of our x. Sorry about the bell there. The slope is negative 0.1629. The interpretation is the predicted price of a Ford F-150 goes down, that's where the negative comes in, by about 16 cents for each mile. So remember, this is miles driven, so 1 unit is 1 mile, so we're talking about each mile. And I rounded this off since this is money, and I said it's about 16 cents. It goes down because it's negative there. We can also make predictions using our regression lines. So not only can we interpret our regression line and see that our selling price for our truck goes down about 16 cents for each mile, we can actually use it to predict the cost of different dollar amounts. So I don't actually have a truck in here that was driven 100,000 miles. It would be about right there. I can actually predict that using my equation. So I'm going to do 38,257. That's the starting price for a truck that's been driven 0 miles. I'm going to subtract about 16 cents for each mile, and we're going to predict what that means if I've driven 100,000 miles. Order of operation says that we multiply first, so I'm going to do 0.1629 times 100,000. Be careful about your number of zeros there. I get that the original price was the original price for 0 miles was $38,257. It's going to go down after 100,000 miles by 16,290. So we're going to subtract those, and I get $21,967. So my predicted cost for a truck that has been driven 100,000 miles is $21,967. Excuse me. It is unlikely that if we found a truck that had been driven exactly 100,000 miles, that it would cost exactly $21,967. It's a predicted amount. It's not going to be perfect. None of those blue dots in that picture actually fall perfectly on the line. We are making predictions here to get close. So let's talk about extrapolation. Can we predict the price of a Ford F-150 with 300,000 miles driven? We can certainly substitute 300,000 into the equation of the line. That is entirely possible. But it is important for you to understand that that's outside the scope of our data. So we end up getting a negative number, which doesn't make any sense. What that means is we're unlikely to find a truck that has been driven 300,000 miles. It is far outside the scope of our data. So that tells me that this is not a realistic prediction. You're not going to pay someone to take your truck off of your hands unless it's to like the dumpster. Extrapolation is the use of a regression line for prediction far outside the interval of x values used to obtain the line. So I only looked at trucks between 0 and 160,000 miles. Using 300,000 is risky, and that causes us to end up with answers that don't make any sense. Such predictions are often not accurate. Even when we are not extrapolating, our predictions are seldom perfect. For a specific point, the difference between the actual value of y and the predicted value of y is called a residual. So here's our formula for the residual. The actual value of y that we saw for an actual truck in this case, minus the predicted value of y, that's like what we used when we got our equation, is y minus y hat here. Make sure you've written this definition down before you move on. So let's talk about residuals here. The scatter plot shows the residual for the F-150 with 70,583 miles and an actual price of $21,994. We're talking about an actual blue dot here. This is an actual truck. The actual truck that had 70,583 miles had an actual price of $21,994. If we use our regression line to figure out what the predicted price would be, it's going to be a little off. We take our y-intercept, we subtract the slope times our number of miles, and we get a predicted value of $26,759. All we do to calculate our residual is to subtract the actual number minus the predicted amount. I get a negative here because the negative value means that the price of this truck was $4,765 less than predicted, based on the number of miles it had been driven. It also means that the point is below the regression line on the scatter plot. That doesn't mean that my line isn't accurate or it doesn't work, or that it's not a good prediction. Sorry about the bell again. It just means that we can only get close. We can't often measure things perfectly that are occurring in real life. So let's look at another example. Do cut flowers benefit from sugar in the water? Does adding sugar to the water in a vase help flowers stay fresh? To find out, 2 stats students went to a flower shop and randomly selected 12 carnations. When they got home, the student prepared 12 identical vases with exactly the same amount of water in each vase. They put 1 tablespoon of sugar in 3 vases, 2 tablespoons of sugar in 3 vases, and 3 tablespoons of sugar in 3 vases. In the remaining 3 vases, they added no sugar. After the vases were prepared, the students randomly assigned 1 carnation to each vase and observed how many hours each flower continued to look fresh. So we've calculated our data here. Along our x-axis is our explanatory variable, sugar. Along our y-axis is our response variable, freshness. And they've calculated the regression line for us. The regression line is y hat is equal to 180.8 plus 15.8x, where x equals the amount of sugar in tablespoons and y equals the hours of freshness. So we're trying to predict how long the flowers can stay fresh based on the number of sugar. I can see right away what looks like a positive correlation. It seems like the more sugar we add, the longer these flowers are staying fresh. But let's see if we can interpret this a little farther. Let's first start by interpreting the slope and the y-intercept of the regression line. Start now by interpreting your y-intercept. The y-intercept in this case was 180.8 hours. What that means is, for an interpretation, if I put 0 tablespoons of sugar in a vase, I predict that flower will stay fresh for 180.8 hours. Now let's look at the slope. Your slope was 15.8. See if you can interpret that now. Well, it's positive, so that means the number of freshness hours is going up. Remember, it's for every 1 unit here, so this is 1 unit of sugar. So we would say for every 1 unit of sugar, the number of hours of freshness increases by 15.8 hours. Make sure you have these written down because you can use these as a model to go back and look at. Now let's calculate and interpret the residuals for a flower that had 2 tablespoons of sugar and looked fresh for 204 hours. So we're looking at an actual blue dot here, an actual piece of data. A flower that had 2 tablespoons of sugar and was fresh for 204 hours. That's the actual Y value here. In order to calculate the residuals, we need the predicted Y value. So what that's telling me is my explanatory variable is 2, my X value is 2. So I'm going to calculate my Y hat, my predicted value. That's 180.8 plus 15.8 times 2, which gives me 212.4. Again, that's my predicted value. That's my predicted value. So that's coming in at about right here. So we can see that there's a bit of a difference there. So our actual was 204. Go ahead and look back at your formula for the residual and calculate that residual now. You should have used the formula y minus y hat. So that would have been 204 minus 212.4, which gives you negative 8.4. See if you can interpret that value now. Your interpretation should have been that the actual value is 8.4 hours below, because of the negative, the predicted value. A residual is just telling you how far off our prediction is. That's it. So our actual value is about 8.4 hours below the predicted value. Would you be willing to use the regression line to predict the hours of freshness for a flour that received 10 tablespoons of sugar? Explain. So let's look at our x values here and think about this in terms of extrapolation. Go ahead and put your explanation for this down now. You should have said no. The x values, or our explanatory values, are between 0 and 3 tablespoons of sugar. Sorry for my sloppy handwriting there. 10 is too far outside our domain, or the scope of our data. Maybe that much sugar becomes harmful after a while. There is probably a point where too much sugar is bad for these flours. We would need to do more testing to figure out what if 10 tablespoons is a reasonable amount of sugar for that. So no, I would not be willing to use the regression line to predict the hours of freshness for a flour. I could, but I think it would likely be unrealistic. Probably the flours won't last as long as that will show. At this point, you should be able to make predictions using your regression lines, keeping in mind the dangers of extrapolation. You should be able to calculate and interpret a residual, and you should be able to interpret the slope and y-intercept of a regression line.